Okay, in this video, I'm going to look at the Grand Canyon, specifically this expansion bar that's above the Grand Canyon. Now, I did a short video on this where I show how this is a feature of expanding water. And that being upstream of the Grand Canyon gives us a catastrophic interpretation of the Grand Canyon, being that this channel is just about 13 miles wide. Now, this is not a feature of a meandering river that slowly carved this. This is showing the exact width of the river of this expansion bar feature. Just like this river here, all the way down here, it's cutting the exact width of the stream. That's how streams work. So therefore we can see how there's basically two rapid recessions. This being a terrace, this was once the bottom. This also was the bottom. And now down here is the bottom of the river valley. So we can see 1, 2, 3 steps. Now, anytime you see a cliff isn't there just out of randomness. Many times it's indicating either a marine terrace or a river terrace. But this cliff on this side is one bank. And then when we go to the other side, we have another cliff and another cliff here. So these are actually cliff and terrace step sequences, just like what you'd find in a river, from a decreasing river. So these are terraces here. Okay. So now that we know that, we can see how wide this was. 26 miles wide. So this is a 26-mile wide channel. And then the Grand Canyon, it's got a lot of tributaries, but can estimate it around, 8 or so miles across. And look at how these tributaries are reaching across here. They're working backwards, right? So when you have erosion off of a cliff edge, this ravine works backwards until they just about almost connect. Okay, let's look at one more river terrace so that you guys can figure this out. This is a clear terrace line here, or a clear cliff edge. Terrace here and the terrace here. And a lot of sharp ravines in here that are actually directional. I really like this terrace here because this canyon, how was it cut? Was it cut over millions of years? Or was it cut from a rapid decrease in water level? Well, the water level was once here. And it made a curving path here. Washed in around here. And then the rest is the Grand Canyon. But when we go over here, we find another cliff edge indicating a water level, and another cliff edge indicating a water level. Zoom in, and within the cliff edge you have terraces on it. So it's terraced and terraced. And let's go here. All right, so what do we see here? All right, can you guys start to spot them now? This is a cliff edge, very straight lined. This is a river channel. That was 5.8 miles wide. And then it kind of just disappears. But even though it's not preserved everywhere, this still is a feature of erosion. and it's worth noting that. Let's zoom in here. And these are mounds, the world's most widespread geologic mystery. And the reason why they're all over the world, at all elevations, all latitudes, all continents, is because whatever formed them happened that vast. And it's fluvial origin, I'll let you know. Let's check out this part of the Grand Canyon. This right here is a cliff edge, distinct line. So look at how abruptly the Grand Canyon ends. Right, so this is all Grand Canyon. You got the expansion bar. It's kind of flat here because this was all underwater. Then you get through here, all those tributaries, all those crazy ravines and terrace steps. And then you keep coming, it comes around, and then it just stops. You've got a flat line across and it stops. Well, this could be a terrace line. And it looks like this is a terrace line, or a cliff line here. Now let's look at these ravines. You see how these ravines are directional and parallel? Parallel ravines are formed from sheet water flow. So water was flowing through here. This was once a valley, filled, a little over 6 miles. That's why you get the parallel ravines. Then you come in here, then you have the bigger terraces, right? But this is a terrace within this terrace. After this, formed here, and then it formed here, and then it formed here, and it's all dry now. But of course, when it floods, you get a flash flood, you're gonna get something like that. So it was once here, and you can be skeptical about this, but I'm telling you, it was once from there to there. That's why all of these ravines are parallel. Okay, you can find parallel ravines all over the world. Now, I want to talk to you about this cliff edge, because this is essentially a marine terrace, or a river terrace from a current coming across here. But the way it's ends so abruptly, it's almost like a marine terrace. Let me just show you one of my favorite terraces real quick. San Clemente Island is just full of terraces. These are all marine terraces. Whether it's a river terrace or an ocean terrace, they're both formed from a current running across them. But you see all these little steps, cliff and terrace step sequence. Really cool stuff. Okay, so there's a lot of detail on this island. Like this here, that's sick. So you got 1, 2, 3, 4. So you can count them and know exactly where the ocean was touching it and exactly where the ocean was eroding it in each of these spots. Tells us where it was, and it tells us water level. Okay, so that's, erosion 101. So when we come back here, same type of thing. There was a current that ran across here, made an abrupt cliff edge. We go back here, find another one. We can go over here, find another one. Right, so this looks just like some nice mounds on a nice fluvial fan deposit. So yeah, this looks just like a river terrace, but there's no other bank. It just goes lower in elevation. Well, just because it goes lower in elevation doesn't mean this isn't a cliff made from the water. If you hold true to the idea that this is a terrace, then you would just assume that the water kept going, and it was all the way across here. All right, so I'll show you this again. That terrace, this terrace, then you can go, you know, these terraces. These you can call these river terraces or marine terraces. I think both would be accurate because of how vast they are. Now, when you check out, oh man, this is the spot here. You ever heard of the grand staircase? Well, the reason why it's a staircase is because it's a cliff and terrace step sequence. It's a massive set of terraces. These are marine terraces, so I'm going to let you know. So let me just count the steps here. Say 1, 2, 3, 4, 5. It's kind of hard to see because they're eroded. But if you study the geology, all of this geologic strata is laid down relatively flat. So when you go up these terraces, you can just go right up the geologic column. And it's incredibly useful for understanding geology, is these terraces. You can just go right up the geologic column. But man, this is a sick feature. Must have been made by the wind. Just kidding. So here we can see how, so this part of the feature came down here and made a nice rounded fluvial fan type of deposit. And there's kind of two of them really. But this up here isn't a fluvial fan deposit. It's a sediment lobe formation that was actually pushed uphill. These sediment lobes are directional, and this indicates an uphill current direction. That's just what it does. And then we can see that it's got ripple formations on it as well. It's a common thing to find on sediment lobes, and the wavelength is 1/4 mile. So that's a cool spot. What the heck is this? Oh man, now I'm confused because I thought these were fins from tectonic forces, but we know that the grand staircase is a bunch of very flatly laid out sedimentary strata that hasn't been deformed much at all. Go over here, it's not deformed either, but it has all of these fins, as if the theory of the tectonic forces has anything to do with it. It can't be true because these are cut in cross grain. Let's look at the strata. Okay, there we go. Beautiful strata. Oh man. No, this is too good. You see what this is? This is cross bedding. I gotta tell you about cross bedding. I can't tell you about it right now. It's too complicated. But I'll just let you in a little secret. It's got to do with moving sediment lobes. Ooh. And then a reversing current to get this flat top, and then it repeats again. But man, that's a sick spot. And then, so this is the erosion. That's the deposition. The deposition's crazy. And then the erosion on top of it is straight up current ruts, indicating sheet water flow. Coming across here in line with a bunch of salt plains, as if they may have anything to do with it. I'm not sure. And then look at these accretion ridges. They just go all the way up. But when you get into this area, even though it's completely covered in salt and it has catastrophic features all over it, all right? So you can find, big old sediment lobes. You can find ripples. You can find mounds. You can find terraces. Let me see if I can find a spot off the top of my head here. Yeah, so these are mounds, each subdivided from a water current. And we got the terraces going up. You know, you can see the U shape. These are really thick ridges as well. And then you got mounds on the ridges. That's a common feature of mounds. You can find that in Lake Missoula and in Ethiopia at 8,000 feet. So it's an interesting thing to find. Yeah, like this right here. Oh yeah, that's what I'm talking about. So there's an idea of the Bonneville flood from, you guessed it, glaciers. Yeah, glaciers must have done it. So look at this, accretion ridges with mounds. Mounds all over these guys. Crazy lake shorelines. Just look at that. So pronounced. So this was pushed back, pushed up into a berm. So it's not just a water current lapping the shoreline with a little bit of, you know, lakeshore wind. No, this was very catastrophic. And let's see the elevation here. 1,590 meters. And then let's go to the bottom here. Oh, let's just do here. Conservative estimate, 1,278 meters. So the difference in elevation, it's a few hundred meters, right? So 600, 700 feet. And it's all the way down, catastrophic and clear rapid decrease. All of these are indicating a rapid decrease. So that's why they say, oh, Lord, there was the Bonneville flood from, you know, glacier meltwater. But how are they always talking about glacier meltwater when it's, you know, salt deposits everywhere? So how did all this salt get here? The Washington scablands are covered in salt deposits. The Ethiopian scablands are covered in salt deposits. Africa. Don't even get me started on Australia. Let's go to Ethiopia. Okay. So this is the salt scablands I was talking about. So parallel to the Dead Sea, you would have these current ruts, these parallel canyons, right? These being current ruts, these being parallel canyons. Kind of parallel, kind of curves a little bit. But for the most part, they're parallel with the Dead Sea. And they're filled with salt, so it's not too much of a stretch to say that it was the ocean current that ran through the Dead Sea that carved these canyons and all of these current ruts. And if we accept that, and accept that there was an ocean current so powerful, it created a canyon 4 miles wide, several hundred feet deep. I mean, this thing looks really deep. Then it's not too much of a stretch when we go back to, you know, the Bonneville area to say, well, maybe all of that rapid decrease of lakeshore lines was kind of like the same thing. Okay. Now, did you know there's a Grand Canyon in Ethiopia? Look right there. You see what that is? It's an expansion bar. And this right here is the canyon. So let me go back to Arizona. Okay. So this is the Grand Canyon. This is the expansion bar, almost 13 miles wide. This is Ethiopia. It's got an expansion bar about 12 miles wide. Or let's see exactly, 12.3. And then this canyon is right next to it. It's right here. This was all removed by water. Almost 30 miles wide. So this is a 30-mile wide canyon. And then once I get over to this area, it's really looking like the Grand Canyon, full of crazy stuff and crazy river terraces. All of these indicate the exact water level as it decreased. And yeah, this is the Grand Canyon. And it comes through here, and then the elevation gets so low you can't see anything crazy because all the crazy erosion happened at higher altitude. That's just a feature I've, come to find commonly. If you want to find the craziest erosion, you don't go low altitude, you go high altitude. It seems kind of counterintuitive, but it just seems to be what Google Earth shows me, and I'm just guessing that it's correct. Because I've never been here. I've never been to Ethiopia. All these terraces. I mean, look at how tiny the current river is. It's not even there. It's a trickle. Steep and narrow V shape. Then we can see that this got so flat because it was the river bottom. Then above it, this also was flattened because it was also the river bottom. And this right here is also flattened because it was also the river bottom. And then it takes you basically all the way to this here, perfectly flat. So there's so much erosion, but it's so focused. Because if it was, the uniformitarian model of erosion, where it's, deep time and rainfall and freeze thaw and all that, this is not what you would expect. You wouldn't expect to get large areas perfectly flat and basically untouched, and then, a 12-mile wide expansion bar. Right? That's just not. It's just not uniformitarian at all. So sometimes you just gotta scrap the theory and, just listen to the terraces. That's all I'm saying. Don't listen to me. Listen to the terraces. I don't know what I'm talking about, but the terraces, they might just know. You know what? I wasn't going to do this, but I'm going to have to take you to South Africa. Because I mentioned terraces, and I want you to know what a real terrace is. See how good my memory is. See if I can find this. Well, I didn't find it, but I found something just like it, basically. These are all terraces. Right? Oh, wait, we find the same dots, the same mounds like we would find on an accretion ridge. And we got such detail. These are almost like a little accretion ridges all over these. I've never even been here before. And you just keep finding cool stuff. Okay, I'm going to find the cool spot though. I'm taking you to it. Hang on. Ooh, what's this? We're getting close. We're getting close. We're getting terracey. That's a technical term for an area with lots of terraces. Very terracey. Let's get on top of the mount. See some mounds, looks like. Let's see, what do we find here? Oh, what are these ripples? What is this, salt? Anybody mining salt out of here? Let's check out these ripples. These are kind of like, remind me of Australian ripples. Let's check out these. Boom, boom. Quarter mile, unimpressed. Not impressed at all. Need something bigger. Comes around. Now see how there's nothing really around this feature here. They're all kind of washed around it. That's something you would find like if you look at a beach rock or a rock around sand, the water washes around it. Or if you step in the sand and the waves wash back and forth and your feet, the sand gets moved away from your feet. That's basically the same thing that's happening here, right? You can find this all over the world, Australia, Arizona. Same thing here. And then plus you get it into a streamlined shape. Streamlined. And then not only do you get streamlined stuff, but you get troughs dug out. So a wind isn't going to dig out a trough and fill it with salt. That's just not something that's in the cards for a wind to do. Okay. I'm always letting you know what wind cannot do and what glaciers cannot do so that we can understand the erosion of the earth. That's the motto. Find some more ripples. Ripples with mounds on them. Let's get a wavelength. Half mile, we're getting a little bigger. Make it bigger. Ooh, perfect lakes. What is that, salt? Taste the seasoning. Yeah, these are nice ones. Nice little salty scours. Nice ripples. I'll take them. All right, you know I can't find it off of... It's really cool. Oh my gosh, I found it. Don't worry. This is one of my favorite terraced areas in the world. First of all, it's covered in mounds. Really nice, well-pronounced mounds. These are not from gophers. Okay, these are not burial mounds. These are from fluid dynamics. You get some really nice cataracts. All right, let's get a little cataract check. Quarter mile. Not bad. And we go up the terraces. We still find mounds. So cool. These ones here kind of spilled off. Get a little bit of spillage action. Pardon me. Very unprofessional. Very unprofessional. See how these mounds are kind of located in a tight pattern? Have you heard of the word accretion ridge? Ooh, nice ones. Yep, this is my favorite terrace right here. Now, the only thing that's... So here's the thing. Would you say this is the Grand Canyon? Or like the Grand Canyon? Yeah, it's just like the Grand Canyon. But it's in South Africa. How can this be? How can you have a Grand Canyon in South Africa? Well, how did the other Grand Canyon form? Well, this was all a lake, right? This is, I don't know if people are accepting this or not, but it's one of the better theories I've heard for the Grand Canyon's explanation. I guess they understand that that this is a terrace and this is a terrace. I don't think so, but maybe they do, and that this is a terrace. And that basically the theory is this was a lake. It sat like a lake. Then it finally spilled over. Ta-da, Grand Canyon. Yeah, I don't buy that because it's way too impressive. But let me just throw a monkey wrench in the whole thought process. Show you how these drumlins are kind of like sediment lobes that indicate an inland current direction. How fun is that? I love it. So you got your little terraces. These are all sudden ravines, okay? Because they're cut into the cliff edge. That's what a sudden ravine is. And then this, you could say by wind, but I'm letting you know, it's water pushed right through here and up. Now, let me show you a real cool spot if I can find it. There she is. So, would wind do this? Think about this. Wind make this? Think wind could do this? Well, no. We can't. So, yeah. So all these features of the way the sand is orientated, that's not, these are relatively still. I'm sure they move a little bit. There's features like this, in certain coastlines that move because of the trade winds and all that. But even if you think, okay, all of this sediment, that's all from the wind. Well, seamlessly with this sediment is this feature here, which was dug out. How hydrodynamics works. When you have an obstacle here, you get turbulent circles, right? You've maybe seen that design or that, what do you call that model, where an airstream comes and then it creates a line of turbulence, goes around it. That's what this is. This is deep erosion. It's not made by the wind. This is a terrace. How'd it get so flat? It was at the bottom of a river. I only say river because it was moving water. But you guys are figuring it out. Leave a comment if you learned anything at all in this video. And then when you find sediment lobes in wet areas, that makes them less likely to be formed from the wind because it's just harder to do physically. And you can just keep following these in. And then you think, oh, these mesas must have been the only remnants left from whatever carved out everything else around it, since they're all kind of streamlined and stuff. Looks like they got some sediment lobes on them. But where's the cool one? Yeah, we keep going inland. And we keep finding sediment lobes until they're drumlins. Drumlins, these are like the drumlins in Mexico. Want to see the drumlins in Mexico? Hold on. Drumlins in Mexico, here they come. Boom. Now you know. Kind of fit in with this ravine here. Kind of get that parallel motion. And all this salt, right? There was a glacier outburst flood that came right through here and made these drumlins, I'm telling you. That's what I think. Yeah, this is ice area. Yeah, we had a big ice age. Big old ice age went through here. You should have seen it. And then you know what the ice also did? It made these badass eskers right in these river channels. Right, these aren't ripples. It would be impossible. This river channel is actually, let's check out how wide this river channel is. 1.5, I'll take it. Very, very interesting terrain. And I like this, the way this comes across here. It's cut across. Reminds me of Chile. The island in Chile, actually, my last video was on that. So an ocean current kind of ran across here, just like an ocean current ran across here and went right through here. Ocean current went across here and cut that out. Let me just zip down here real quick, show you exactly what I'm talking about, like this. Ocean current went right in between the, to isolate and make all these, turn them into islands. And then of course that is just like what we find up here, particularly Vancouver Island, all cut off and streamlined. A bunch of accretion ridges from the ocean current. All right, these are pretty serious accretion ridges, very distinctly shaped. So we can see, and this curve right here is from that stream. This is all kind of cut out, come through here. Then you have the other stream coming through here. You've got these mega channels, and these were all carved by, you know, debris flows, mud flows. You know the story. What was I talking about? Arizona? What's there to talk about? Oh, I know something. I like this guy here. So let's imagine the uniformitarian model. Long time, deep time, lots of rainfall, and nothing else. Why is it that this here, you know, this is, wait a minute, this is a U-shaped valley. This was made by a glacier. Okay. Now, let me let you know. So let's get a width check, 1.2. Okay, so we got a decent little valley here. Here's my question for my uniformitarianisms. Why is it 1.2 miles wide here, deep U-shaped valley? And then down here, a narrow ravine. That's tiny and little and, you know, what is it, a tenth the size? Less than a tenth the size? Yeah, a tenth the size. How'd that happen? If you have an answer to that question, you have to leave it in the comments. I'm trying to get a dialogue going. So please give that a comment. If you made it this far in this video, you know, I salute you because I'm just going all over the place. Just freestyling the erosion of Earth right now. I mean, I could spin the world. Let's see. I'm going to spin the world and just find a cool spot. My eyes are closed. Okay, here I am. Great, I'm in a green spot. Those are the tough ones. Oh wait, I know where I'm at. I'm in Russia, aren't I? Look at all these scours. Oh, this was a good one. I swear my eyes were closed. Very directional, right? What's the direction? The direction, at least for this big one here, right? All of these features probably went back and forth, but this one shows this way is the direction. And then look at the smaller one is directional the other way, as well as this one and this one. So that's actually a common thing. You find bigger features being a directional one way, and then the smaller features being a directional the other way. Now that's a little tricky note you got to put in your notepad, because it's a reoccurring theme that must be understood. Plus the fact that there's a lot of seasoning. So let's see exactly where I'm at. Yeah, so we go over. Are there any drumlins over here? So we got all this seasoning over here. But how to get there? How did we get all these ruts? It's whenever you find something this texturized, it's probably a scabland. And if you find a scabland, flip a coin. About 50% of the time, it's going to be a salt scabland. And that's got an implication to it. Let's see. Yeah, so then we get into the drumlins. Really nice ones. Parallel salt ruts. Gotta love them. Now let's check these out. So why are these so organized? Oof. So these are parallel features, right? These big channels are parallel channels. You can see it with a topographical map. What do we find? What forms perpendicular to the parallel path? That's it. Ripples. Where do we find ripples? Wait, come on. I know you're around here. These are the ripples. Where are the ripples? Where are they? I know you're out here. You can see the ripples on a topographical, actually. Drumlins, right? So these are parallel. Just like the parallel ravines. And then these are perpendicular. These are perpendicular landforms. That's an indication of ripples. I found a nicer set of ripples. I must have lost them. Oh, here we are. Okay, so check out these ripples. These are nice ripples here. All right, they've got an elevation to them. You can check them out on topographical. Let's get a wavelength, beginning to beginning, 1.27. I'd say that's impressive. 1, 2, 3, 4, 5 really nice ones. And then they kind of get a little messy. But you can still see them. And that's perpendicular with these parallel channels. Now this feature here, this big beautiful lake, which kind of looks like a flower about to bloom or something. This is a directional feature, right? So what did I tell you about the Carolina Bays? You've got the scarp edge, then you've got the tail. Now this tail goes straight into a channel. So, but it's not just that channel. If you look closely, you can see there's another channel this way as well. And then it leaves this as like a streamlined shape as well. And yeah, all this ice got left behind from all the glaciers, because ice can hold a lot of salt. Just kidding. Now check out these lakes here. These are actually in a pattern as well. And you kind of see a horizontal pattern to these lakes. Just like the horizontal pattern of these ripples. These are a feature of an undulating current. Just like you can find... Alright, I'm going to have to go to Australia to explain this to you. You know this is my favorite spot right here. Okay, so a water current comes across, makes this, comes across, makes these big channels. When the water current's flowing over here, and it's carving this, and it's carving these ripples and their troughs, it's digging out the trough, It also digs out a perfectly circular, or not perfectly in this case, but many times it can be, a perfectly circular little lake, little trough. Now, water has some interesting features. It's not like a glacier that's very still. It's got a lot of motion. It's got a lot of inertia. It's got an undulating force, right? The undulating force is what makes the ripples and digs the trough. So imagine a sinusoidal wave. It's got the undulating force, and it's also got a coalescing force. Coalescing force means it comes together and forms tight ruts. But when you have a coalescing force within this undulating force, boom, that's the circular lake. Okay, I'll explain that again with more detail, but hopefully you guys understood that. You've got the undulating force, and then when that undulating force coalesces, it digs a nice little circular trough. And that's why you can get lines of circular lakes, right? See that? Same thing here. Exact same thing. And this is filled in with salt because, well, the ocean was right here and the ocean carved it out. Well, let's just keep that same energy when we're in Russia. And we see all these incredible features. Okay, that's it. I've told you guys too much. Now I gotta go. Thanks for watching. Please like, subscribe, share, and tell everybody you know. Okay, bye.